We will continue our discussion on gear trains. In this lecture, I am going to discuss about epicyclic gear train, their kinematics and torque transmission. Then epicyclic gear train, as I have mentioned that there are gears whose centers can move or rotate in space. This is unlike the simple and the compound gear trains where their centers are fixed. The epicyclic gear train has these components. It has got a planet gear which is mounted freely on an arm and it rolls on what is known as the sun gear. This is the analogy is from our solar system. So, here I have a sun gear on which there is this planet gear which meshes with the sun gear. The sun gear axis is fixed, which is indicated by this cross at the center, while the planet can roll freely on the sun gear. In order to keep the planet in place, we have the arm. So, that keeps the planet in its place as it rolls on the sun gear. So, the planet axis rotates with the arm as it is shown here. This system has 2 degrees of freedom. Let us understand this. If I want to fix the configuration of the sun planet system, sun planet and arm system, then suppose I fix the angle of the arm, I fix the angle of the arm. So, that is 1 degree of freedom. I can arbitrarily choose the angle of the arm. Suppose I fix this, then still the sun and the planet can rotate with respect to one another. Therefore, if I fix the sun at a particular angle, then the planet also gets fixed. Therefore, I can fix the arm and the angle of the sun to fix the whole system. So, this has 2 degrees of freedom, since we require 2 variables to fix up the configuration. Now, there are 2 variants as we will soon see. We have this external sun, external gear which is the sun, or an internal gear which is a ring gear. Here is an epicyclic gear train with a sun gear. If you look at the representation, a schematic representation of this, the sun gear axis is fixed, whereas the planet is mounted freely on the arm. The arm can rotate. So, therefore, the arm carries the planet as the planet meshes or rolls on the sun. This is the second type, in which we have a ring gear. So, this is an epicyclic gear train with a ring gear. This is an internal gear. So, the ring gear is an internal gear. If you look at the schematic representation, this is the ring gear and we have the planet mounted freely on the arm. Let us now look at the kinematics of the epicyclic gear train. In order to derive the relation between the input and out, now we know that there are 2 inputs and 1 output, there is 2 degrees of freedom. Therefore, we consider this contact point C of the pitch circles of the sun and the planet gears and try to do a velocity matching at the contact. This is for pure rolling. Now, if you look at the velocity of the point C as seen from the planet gear side, this can be written as velocity of the contact on the planet is equals to velocity of the center of the planet and plus omega cross omega planet cross the radius vector. Let us look at these vectors one by one. V p, which is the velocity of the planet center, this is the velocity of the planet because of the rotation of the arm. So, this velocity V p is because of the rotation of the arm. Then we have, because of the rotation of the planet itself about its center, we have this is omega planet cross the radius vector, and if you do this calculation and finally write out this vector equation, then it turns out that because these two vectors are in opposition. So, velocity of the center of the contact point, velocity of the contact point C of the planet is equal to velocity of the center of the planet minus omega p times r p. Now, velocity of the center of the planet, this vector V p, which I had drawn, this is V p. As I have mentioned that this is because of the rotation of the arm. So, this must be equal to, so omega of the arm cross the length of the arm, which is summation of these two vectors. So, one is radius of the radius vector of the sun and this vector, the radius of the planet. Therefore, if you express velocity of the center of the planet, it will be omega a times sum of the radii of the sun and the planet and minus omega p r p. If you look from the sun side, then velocity of the contact from the sun side is equal to omega of the sun times the radius of the sun. So, this is omega of the sun times radius of the sun. So, that is the velocity of the contact when you calculate it from the sun gear side. Now, these two must match because these two pitch circles are in pure roll. If you do that, then omega s r s must be equal to omega a r s plus r p minus omega p r p. Now, if you simplify this expression, you can write this as omega s minus omega a times r s is equal to minus of omega p minus omega a r p. So, therefore, now I can take the ratio, let us say omega p minus omega a by omega s minus omega a, that is equal to minus of r s by r p, and this you also know is equal to minus of n s by n p. So, this relation that we have obtained relates omega of the planet, omega of the sun and omega of the arm in terms of the number of teeth on the sun and the number of teeth on the planet. So, this I write out for you. So, this is the final expression of the motion relation. From here, given let us say omega of the arm and omega of the sun, you can find out omega of the planet, or given the omega of the planet and omega of the sun, you can find out omega of the arm. Let us now look at the other case where you have a ring gear. So, here you have this relation from similar considerations, that omega of the contact as seen from the planet side, this must be equal to velocity of the center of the planet now plus omega planet times radius of the planet. So, from the planet side, if you calculate, velocity of c is equal to velocity of the center of the planet plus omega p times r p. Now, velocity of the planet is nothing but omega arm times this length. Now, this is the velocity of the planet. So, this vector is V p, that is V p. Now, V p is equal to, if I call this L, V p is equal to omega arm times this length L. Now, this length L can be written as radius of the ring gear minus the radius of the planet gear, radius of the ring gear minus radius of the planet gear, and that has been substituted here. This term comes from here, and we match the velocity of the contact from the ring gear side, which is omega r times radius of the ring gear. If you simplify this expression, we have this relation, and you can write this ratio of the on the right hand side R r by R p as N r by N p. Here you should notice that because this ring gear being internal gear, the sign here is positive. This is unlike the relation we obtained when we had a sun gear. So, that completes the kinematics of the epicyclic gear train. Let us now look at the combination of both a sun gear and a ring gear with a planet. Now, this is the fundamental unit that is used in automatic transmission, as we will discuss. This is the schematic representation of the gear train with this combination of ring and the sun. Let us now look at this kinematic relations and go in pairs. We will look at these this combination in pairs. First, let us look at the sun planet pair, which means we are looking at this system in which we have the sun, planet and the arm. We have derived the kinematic relation, which is of this form. Next, we look at the ring planet combination. So, this is a ring planet combination. So, we have the ring gear, the planet gear and the arm, and the kinematics for this we have derived as written out here for you. You can clearly note the difference in these two relations. Now, if you divide one by the other, then you can find out this relation between omega sun, omega arm, omega ring in terms of the teeth, number of teeth on the ring and the sun. You will notice that this does not involve the planet anywhere. So, you have a relation between the angular speed of the sun, the ring and the arm in terms of the number of teeth on the ring and the number of teeth on the sun. Now, let us look at torque transmission. Here I have drawn out the torques that are acting. Tau r is the torque on the ring gear, tau a is the torque on the arm and tau s is the torque on the sun. If you do a power balance, then this is the relation we have been looking at, this relation. If you do a power balance, then the net rate of work done on the system must vanish. There are three inputs, so to say. You have the power input at the ring, the power input at the arm and the power input at the sun, and the total power input must add up to 0. That gives us our power balance, and we also have the torque balance relation, because the whole thing is in equilibrium. We are assuming that whole thing is in equilibrium, there is no dynamic forces acting. So, everything is in steady state. So, what do we have finally? We have 2 motion inputs and 1 output, and we have obtained 3 equations in 6 variables. So, what are these 3 equations? One equation was the kinematic relation between the omega sun, omega ring and omega arm in terms of the number of teeth on the sun and the ring. The other equation was of power balance. So, the power input at the sun, power input at the arm and the power input at the ring, they must add up to 0, and the torque balance. These are the 3 equations we have. In 6 variables, the 6 variables are shown in this figure: omega r, tau a, omega a, and tau s, omega s. Now, if we are given 3 of these variables, then we can solve for the other 3. If you quickly go back and look at this motion relation, let us say, if we are given the omega of the ring and omega of the arm, then from this relation we can solve for omega of the sun. So, we can solve the omega of the sun. Let us look at some very special cases. Let us say that I fix up omega of the arm as 0. Let me take some special cases. One special case can be omega arm is 0, which means my arm is fixed, it is not rotating. If omega arm is 0, then we have this relation omega s by omega r is minus of n r by n s, which means it is a simple transmission between the sun and the ring. I mean, what we have for 2 external gears. On the other hand, if you let us say fix the arm with one of the gears, let us say omega arm is equal to omega sun. Suppose I fix the arm onto the sun, which means I fix this, then omega arm and omega sun, they are equal. If that be so, then this whole thing vanishes, this becomes 0. Therefore, in order to have this relation valid, this also must be 0, which means that the omega of the ring gear must be equal to omega of the arm, and that is equal to omega of the sun. Therefore, all of them are matched. Therefore, if I fix the arm onto, let us say, the sun, all the shafts move at the same angular speed. So, omega all the gears move at the same angular speed, omega r is equal to omega a is equal to omega s. If I let us say fix the ring gear, let us say if I fix the ring gear, which means I do not allow this to rotate, then I have this relation omega sun minus omega arm by minus omega a is minus n r by n s. So, under various combinations you can calculate the relation between the gears, the angular speeds of the gears. So, let me conclude by summarizing what we have discussed. We have looked at the epicyclic gear train, their kinematics, considering both a sun planet gear and a planet ring gear and a combination of these two. We have calculated the motion transmission and the torque transmission ratios. So, with that I will close this lecture.